Imagine a moment before stars, before galaxies, before time had any rhythm at all. A moment when the universe itself was nothing more than a trembling sheet of potential energy, vibrating toward existence. Now imagine that the tremors never stopped, that the universe, vast and seemingly serene, might still quake, not metaphorically, not poetically, but physically, structurally, violently, just as Earth does. What if every filament, every cluster, every void between galaxies quivered with ancient echoes? What if cosmic quakes, unimaginably massive, ancient and terrifying, shaped everything we see? That question confronts a possibility so strange, so overwhelming, that even the most seasoned cosmologists hesitate before attempting to answer it. Because to consider that the universe has quakes is to question the stability of reality itself. It suggests that the cosmic web, the largest structure ever observed, might shift, flex, snap, or resonate on scales beyond ordinary comprehension. It forces us to ask, what if the universe is not calm? What if it never was? To understand this idea, we must start someplace familiar. Earth. Our planet quakes because it is alive with motion, molten layers circulating, tectonic plates grinding, stresses building until they release in abrupt, catastrophic bursts of energy. Earthquakes are reminders that the ground beneath us is not solid in any absolute sense. It is fluid, restless, driven by forces we can only partially control. But what is Earth except one small structure within a structure within another? What if quakes don't end at planetary scales? What if they extend to stars, to galaxies, to the universe? Cosmic structures are not static. Stars quake, white dwarfs tremble. Neutron stars, those ultra-dense, city-sized remnants of stellar death, vibrate and crack in ways that release more energy in a fraction of a second than our sun will release in a century. These are called starquakes. They are real, measured, and terrifying. Some come from the solid crusts of neutron stars snapping like titanic plates of nuclear matter. Others ripple across stellar surfaces like ocean waves of plasma. Starquakes can alter rotation rates, distort magnetic fields, and unleash bursts of gamma radiation powerful enough to sterilize entire planetary systems. These are the smallest quakes in the hierarchy. Above them are black hole quakes, subtle but detectable tremors in the warped space-time around collapsing stars. And beyond those, the most mysterious of all, gravitational wave events, cosmic shudders from the collision of ultramassive objects. These waves ripple across the universe, briefly stretching and compressing space itself. But even gravitational waves may be just a whisper of something larger, because when cosmologists map the cosmic web, the vast scaffolding of galaxies woven through 93 billion light-years, they see something uncanny. The structure is not smooth, it is not quiet. It has patterns, filaments, nodes, voids, like fractures. As if the universe long ago cooled and settled like a colossal crust, its internal stresses frozen in place until something shook it. To think the universe has quakes is to imagine that space-time itself can fracture, resonate, or convulse. It implies that cosmic structures might store tension, release energy, or shift their alignment. It suggests the universe might not simply expand, it might twitch, pulse, or rumble. What would cause such a thing? On Earth, quakes come from heat, pressure, and movement within a planet's interior. On a cosmic scale, the interior of the universe is not rock or magma. It is space-time, dark matter, and dark energy, interacting in ways we have barely begun to understand. Dark matter forms a gravitational skeleton. Dark energy pulls everything apart. But what if these two forces sometimes conflict? What if tension accumulates in the cosmic web over billions of years, building until something gives? Imagine a filament of dark matter stretching tens of millions of light years. Galaxies embedded in that filament move slightly, pulled by other structures. Over unimaginable timescales, stress accumulates. Then suddenly, it shifts, not explosively, not like a planet cracking, but as a low-frequency cosmic quake, rippling through tens of thousands of galaxies. Not a sound, not a flash, not a shockwave, just movement, a subtle, universe-scale readjustment of structure. We might never notice such a quake directly. Its timescale could be millions of years. Its effects could be gentle, almost geological in slow motion. But cosmologists have found strange anomalies, massive galaxy rotations that shouldn't exist, galactic clusters drifting as if tugged by invisible forces, cosmic microwave background irregularities hinting at asymmetric energy flows. These could be relics of past cosmic quakes, ancient shifts in the structure of space-time. And then there is something even more curious: the baryon acoustic oscillations, ripples frozen from the earliest moments of the universe, like the fossilized waves of a primordial quake. These enormous patterns in the distribution of galaxies are not metaphors. They are literal pressure waves, cosmic seisms, from when the universe was young and blazing hot. The first universal quakes happened before atoms existed, before light could travel freely. They shook the universe so profoundly that their imprint persists 13.8 billion years later. If the early universe had quakes, why would they stop? Consider what happens as the universe continues to expand. Space is stretching, but not uniformly. Some regions expand faster than others. Some are slowed by gravity. The push and pull between expansion and mass could create stress points, cosmic fault lines, not cracks in the classical sense, but regions where space-time might behave unpredictably. What if dark energy intensifies? What if the expansion rate reaches a threshold where space-time itself becomes unstable in certain zones? Could the universe shudder as it readjusts? Could cosmic filaments shift like tectonic plates? Then there is an even stranger possibility, a theoretical idea called cosmic phase transitions. Just as water can freeze or boil, the universe itself may undergo transitions between different states of space-time. When these transitions occur, the fabric of reality could rupture, releasing gravitational waves on unimaginable scales. These would be the ultimate quakes, universal convulsions marking the birth of new physics. If such events happen, they could reshape the fundamental constants of nature. They could collapse galaxies, erase star systems, or create new regions of space-time. We might never detect them. Or worse, we might detect them only as a distant low-frequency rumble, right before reality shifts around us. But if cosmic quakes exist, we are not merely spectators. We are part of the structure. Every atom in our bodies, every star in our sky, every planet, every galaxy, they are all nodes in this trembling web. A cosmic quake, even a gentle one, would influence gravitational fields, distort background radiation, subtly alter galactic motion. Over billions of years, these shifts could rewrite cosmic geography. Perhaps they already have. Perhaps every structure we see today, a spiral galaxy, a supercluster, a great void, was shaped by ancient quakes that rippled long before life arose on Earth. We assume the universe expanded smoothly, but what if it staggered, lurched, trembled, growing in fits and convulsions? What if the cosmic web is not simply the result of gravity, but of stress points, resonances, and oscillations? What if reality has a pulse? In this first step, we ask only the opening question. If Earth quakes, why not the universe? But we have not yet traveled into the deeper implications. We have not yet explored what evidence might exist, what mechanisms could cause universal quakes, or what dangers they pose. We have not yet asked the most unsettling question: what happens if the next quake is already approaching? Before we go further, you must understand one thing. To accept the possibility of universe-scale quakes is to accept that nothing we consider stable truly is. Not matter, not space, not time. Everything might tremble, everything might shift, everything might, in the deepest, oldest sense, quake. And if it does, then our universe is not a quiet, expanding void. It is a restless, dynamic, living structure, one whose deepest tremors we have barely begun to imagine. If the universe can quake, then somewhere, hidden in the cold depths between galaxies, lurks the evidence, not in the form of shattered rocks or broken crusts, but in patterns so vast, so faint, so stretched across eons, that only a few signals ever reach us. Signals that don't behave like the remnants of explosions or the whispers of ancient light, but something deeper, shifts, nudges, drifts, imperceptibly slow changes in the positions of galaxies, the temperature of cosmic radiation, the structure of space-time itself. To understand what a universe-wide quake might look like, imagine this. You are floating far outside any galaxy, suspended in the endless void. Everything is seemingly still. The cosmic microwave background glows at a uniform temperature, faint but steady. Galaxies drift gently, carried by expansion. Nothing moves abruptly, nothing feels unstable. But then something changes, so slowly that you don't notice it for millions of years. A subtle warping, a faint stretching of emptiness itself, propagating through the void like a ripple passing through a silent ocean. You cannot hear it, you cannot feel it, but gravitational fields shift by a fraction. Light bends slightly. Galaxies adjust their trajectories as if pushed by an invisible hand. This, in its most basic form, is what a cosmic quake would be. A structural readjustment of space-time spanning millions of light years. On Earth, seismic waves travel through rock. In stars, quakes ripple through nuclear matter. But in the universe, waves would propagate through the fabric of space-time, guided by the distribution of dark matter and sculpted by the push of dark energy. The cosmic web would vibrate not with sound, but with gravity. And the first hints that such quakes might be real came not from telescopes, but from anomalies, oddities that refuse to disappear. One of the most puzzling is the axis of evil, a name cosmologists gave, half joking, half frightened, to a strange alignment in the oldest light in the universe. The cosmic microwave background, CMB, should be random, uniform, isotropic, but it isn't. Several large-scale features align along a mysterious direction, a cosmic tilt that should not exist. Some called it coincidence, others blamed experimental errors, but a small faction proposed something different. What if this axis is the scar of a universal quake, a relic of a massive structural shift that occurred billions of years after the Big Bang? If the universe shook on unimaginable scales, the CMB would bear faint distortions, patterns too large to be caused by galaxies or dust, patterns that look eerily similar to the ones we see. And then there is another anomaly, dark flow, a mysterious, large-scale movement of galaxy clusters drifting toward a point beyond the observable universe. Gravity cannot explain it. No structure massive enough exists within the cosmic horizon. Something outside our visible cosmos seems to tug on them. But what if the explanation is simpler? What if their motion is not a pull, but a recoil? What if the cosmic web, vast as it is, shifted long ago, sending clusters, drifting like boats after a distant, unseen quake? The scale is impossible to grasp. A shift of space-time itself would not be abrupt like an earthquake on Earth. It would be a slow flexure, a migrational tremor unfolding over hundreds of millions of years. But the effect, on a universal scale, would be profound. Consider the Sloan Great Wall, a massive cosmic structure stretching over 1 billion light years. Its existence puzzled astrophysicists for years. It seemed too large to form naturally within the age of the universe. But what if these megastructures are not merely the result of gravity clustering matter, but the result of resonances, zones where cosmic quakes amplified density waves, piling matter into colossal filaments and walls? Imagine tapping a massive metal plate. Waves travel across it, converging, interfering, forming patterns. Now imagine the plate is the universe in its early stages, an ocean of plasma and dark matter. Each quake leaves ripples. Each ripple shapes where matter will gather. Over billions of years, these ripples freeze into place, becoming the superclusters and voids we observe. The largest voids, some spanning hundreds of millions of light years, may not be mere accidents. They may be the calm centers between cosmic fault lines, regions where quakes dissipated energy, leaving behind vast empty trenches in the fabric of the cosmic web. But if the universe has quakes, then what mechanism drives them? To find an answer, we return not to cosmic structures, but to the fundamental forces governing reality. Dark energy stretches space-time. Dark matter binds it. Ordinary matter weighs it down. Gravity curves it. Expansion pulls it apart. These forces battle continuously. For billions of years, they have been locked in a delicate balance. But what if this balance is unstable? What if tension builds just as it does in Earth's tectonic plates? The cosmic web may not be a passive structure. It may be under constant stress. Every time a galaxy merges, every time a black hole forms, every time a cluster drifts, the dark matter scaffolding readjusts. Over immense periods, these adjustments accumulate, stress builds, and eventually, something snaps. Not violently, not explosively, but cosmically. A quiver in the scaffolding of dark matter, a realignment of gravitational potentials, a slow, rolling quake across the universe's skeleton. One theory even suggests that the universe might be ringing from such events, vibrating with low-frequency gravitational waves so large that we cannot yet detect them. These waves would be longer than galaxies, longer than superclusters, stretching across billions of light years. Unlike the sharp, high-frequency waves from black hole collisions, these would be deep, powerful, resonant, like the sub-bass of reality. Some have speculated that these universal vibrations could explain why certain regions of the universe expand faster than others, that cosmic expansion itself might not be smooth, but lumpy, influenced by ancient tremors in space-time. These tremors could temporarily accelerate or decelerate the growth of certain regions. In this view, cosmic quakes are not rare. They may be cyclical, recurring, part of the natural rhythm of an evolving universe. But perhaps the most unsettling idea is this. We may currently be living inside the aftershocks of a cosmic quake. Several ongoing anomalies point toward this possibility. The Hubble tension, the disagreement between the universe's expansion rate measured locally and the rate inferred from early cosmic light, could be a symptom of a universe still settling from an ancient quake. The cosmic web may be stretching unevenly, with some regions recovering faster than others. The expansion rate may not be constant across all directions, a possibility mainstream cosmology cautiously avoids but cannot entirely rule out. If a cosmic quake occurred hundreds of millions or even billions of years ago, its effects would still be rippling outward. Galaxies would drift subtly off expected paths. Clusters would migrate slower or faster than predicted. Even the fabric of space-time might appear slightly warped when measured on the largest scales. Such distortions are exactly what some recent observations suggest. Perhaps the universe is not a static grid expanding smoothly. Perhaps it is trembling, ever so slightly. And if that is true, then the cosmos we see today, its grand structures, enormous voids, and intricate filaments, may be shaped not solely by gravity, but by something more dynamic, something restless. The universe might be young compared to the scale of these events. We might be observing not a calm, stable cosmos, but one still vibrating from ancient convulsions, its architecture slowly settling like cooling metal after a tremendous impact. In this emerging picture, cosmic quakes are not destructive, they are formative. They carve valleys in space-time, they shape the cosmic web, they influence the trajectories of galaxies, they determine where clusters form, where voids emerge, and even the evolution of cosmic expansion itself. But this raises a deeper question. If cosmic quakes shaped the universe, what caused the first quake? Was it a natural consequence of expansion, a relic of inflation, or something stranger, something hinting at physics we have yet to understand? In the next block, we dive deeper into the mechanisms that may trigger universe-scale quakes, exploring exotic possibilities, phase transitions, dark matter turbulence, quantum instabilities, and the potential for cosmic fractures in space-time. For now, understand this. The universe we see is not a silent, static architecture. It is a vast, resonant structure that may still be trembling. And if those tremors continue, if the universe has not finished quaking, we may eventually witness the next shift, not in a moment, not in a lifetime, but in the deep future of cosmic time. If the universe can quake, then something must trigger these colossal convulsions, something powerful enough to disturb the very architecture of reality. Unlike Earth, which hides molten rock beneath a fragile crust, the universe conceals no solid mantle, no tectonic plates, no subterranean magma. Its interior is space-time itself, threaded with dark matter, stretched by dark energy, shaped by forces we only partially understand. So what could push such a structure into tension? What could cause stress to build until the cosmos itself trembles? The answers begin in the smallest moments imaginable and end at the largest scales the human mind can conceive. They start with phase transitions, abrupt changes in the state of reality, and build toward cosmic scale restructuring, driven by the universe's invisible components. They reach into the earliest seconds after the Big Bang and extend to the far future, when dark energy tears everything apart. And as we peel back these layers, a startling picture emerges. The universe is not simply expanding, it is evolving, growing, cooling, changing. And in those changes lie the seeds of cosmic quakes. Let us begin with the most ancient and dramatic triggers, the primordial phase transitions. In the earliest thousandths of a second after the Big Bang, the universe was a boiling turbulence of energy and plasma, governed by unified forces. Gravity, electromagnetism, the strong and weak nuclear forces, today distinct, were once the same. But as the universe cooled, these forces separated in violent, abrupt transitions. Each separation unleashed enormous pressure waves across the cosmos. These were not gentle ripples, they were colossal shock fronts, seismic detonations in the fabric of space-time. Their echoes, frozen in the cosmic microwave background, are some of the earliest evidence that the universe was born in a storm of quakes. Could such transitions still occur? Most physicists believe the early transitions were unique, but others argue that the universe may not be finished shifting states. The Higgs field that gives particles mass may not be in its true lowest energy configuration. If it ever changes state, even slightly, it could unleash a universe-wide quake, a phase transition rippling outward at nearly the speed of light. Such an event would rewrite the laws of physics in its wake. This possibility is known as vacuum decay, and it represents one of the most catastrophic forms of cosmic quake imaginable. In this scenario, a bubble of true vacuum forms somewhere in deep space. It expands, and as it grows, it adjusts space-time to its new, lower energy state. Nothing can resist it. Galaxies, atoms, light itself, everything in its path is rewritten or destroyed. Thankfully, if such a transition occurs, we would never see it coming. The bubble would arrive faster than any warning signal could travel. But cosmic quakes need not be apocalyptic to be real. Many could be subtle, slow adjustments rather than immediate catastrophes. And for these, we look to the universe's invisible skeleton, dark matter. Dark matter is not passive. It interacts gravitationally. It forms filaments and nodes. It flows. And wherever it flows, it produces gravitational tides that shape the visible universe. But what if dark matter does more than flow? What if it experiences turbulence, eddies, currents, vortices, on cosmic scales? If large volumes of dark matter collide or redistribute themselves, the gravitational potential across millions of light years would shift. These shifts would propagate outward, disturbing galaxies, altering cluster velocities, and potentially triggering resonances, slow quakes in the cosmic web. Some simulations already hint at this. When clusters merge, their dark matter halos slosh and vibrate like colliding fluids. These vibrations can last billions of years. They generate waves, gravitational, structural, resonant, that ripple outward. On human timescales, they look frozen. On cosmic timescales, they tremble like struck bells. If the dark matter skeleton trembles, everything trembling with it. Now consider another unseen force, dark energy, the mysterious driver of cosmic acceleration. Dark energy is sometimes described as a pressure that stretches space-time. But what if that pressure is not uniform? What if dark energy varies slightly across regions of the cosmos? A differential in the strength of dark energy could create cosmic tension, zones that stretch faster, pressing against zones that stretch slower. This is the cosmic equivalent of tectonic compression. If expansion is uneven, the universe is not stretching like a smooth balloon. It is pulling itself in different directions. Over billions of years, these differences could accumulate as stress. And when the stress resolves itself, a universe quake, a sudden readjustment in the expansion field, sending out waves that alter galaxy motions. This idea grows even stranger when we consider the possibility that dark energy might not be a constant at all, but a field, one that vibrates or undergoes transitions, much like the Higgs field. If dark energy shifts in intensity, even slightly, the entire universe would feel it. Expansion rates would adjust, distances would change, clusters would drift, space-time would tremble. Perhaps the most intriguing evidence for this comes from the discrepancy known as the Hubble tension. Two methods of measuring the expansion rate of the universe produce two incompatible answers. This suggests something in space-time is not uniform, not stable, not fully settled. A cosmic quake, ancient or ongoing, could explain the mismatch. But cosmic quakes need not come from invisible forces. Some may originate in regions where matter is dense, turbulent, collapsing, the interiors of supermassive black holes. At the centers of galaxies lie these titanic objects, millions or billions of times the mass of the Sun. As they merge, collide, or cannibalize stars, they unleash gravitational waves that ripple through space-time. These waves are strong enough to shake entire galactic clusters ever so slightly. If two supermassive black holes collide in a region dense with dark matter filaments, the surrounding structure could quiver for millions of years. Imagine two galactic cores spiraling inward, their event horizons merging in a titanic collapse. The resulting shockwave, though invisible, would turn space-time into a vibrating drum. Waves would spread outward, stretching and compressing entire regions of the cosmic web. The quake would be faint but enormous, its crest spanning thousands of light years. Some scientists believe that such mega-collisions could explain oddities in the alignment of galactic spin directions, as if a cosmic wave once washed across a region, subtly rotating everything in its path. But the strangest possibility of all is this: cosmic quakes may result from fluctuations in the quantum structure of space-time. Quantum mechanics teaches us that even empty space is not empty. It seethes with virtual particles flickering in and out of existence. On subatomic scales, space-time is jittery, turbulent, chaotic, a storm of quantum foam. Normally, these fluctuations cancel out on large scales. But what if, occasionally, they do not? What if quantum fluctuations align in vast regions, amplifying into macroscopic effects? A rare confluence of quantum fields could distort the curvature of space-time, producing a wave, slow, massive, and incredibly subtle, that travels across the universe. This is the concept of quantum gravitational turbulence. If real, it implies the universe is always trembling, always shifting, always alive with microseismic activity, just on scales far beyond our detection. And as if quantum turbulence were not enough, there is another possibility lurking in the mathematics of cosmology: the existence of cosmic defects. These are relics predicted by some grand unified theories, tiny imperfections left over from early universe phase transitions. Imagine the universe cooling rapidly after the Big Bang. If different regions cooled at slightly different rates, the boundaries between them might freeze in place as exotic structures, cosmic strings, domain walls, or monopoles. These objects would distort space-time profoundly. If they move, collide, or collapse, they could generate universe-shaking gravitational waves. Some researchers have even proposed that certain unexplained gravitational wave signals might be faint echoes of cosmic string interactions, brief, intense quakes in the deep architecture of space-time. So we have many candidates for triggering cosmic quakes: primordial phase transitions, dark matter turbulence, dark energy fluctuations, black hole collisions, quantum gravitational instabilities, cosmic defects left from the early universe. But all these mechanisms point toward the same conclusion: the universe is not stable, it is dynamic, unsettled, tense, and these tensions, large or small, may reshape the cosmos on timescales beyond human comprehension. This raises a profound question. If cosmic quakes can occur, could they influence the fate of galaxies, stars, or even life? Could civilizations long gone have witnessed such quakes? Could we, far in the future, observe one ourselves? In the next block, we will explore the consequences of universe quakes, how they reshape galactic structures, influence cosmic evolution, and possibly determine the long-term destiny of the universe itself. For now, know this: the cosmos is not a silent, frozen architecture. It is a living structure, trembling with forces both ancient and ongoing. If cosmic quakes are real, subtle or violent, ancient or ongoing, then they must leave consequences scattered across the universe like fingerprints on glass: subtle distortions, peculiar motions, the architecture of galaxies bending in ways that defy simple gravitational expectation. These consequences may be faint, stretched over billions of years and trillions of kilometers, but they exist. And when we examine them through the lens of a trembling universe, a remarkable truth emerges. The cosmos we see today may not merely be shaped by gravity and expansion, but by the aftershocks of ancient cosmic convulsions. To understand how cosmic quakes sculpt reality, let us begin with their most direct and fundamental effect, the redistribution of matter across colossal scales. In a universe governed by gravity alone, matter should have clumped gradually into a web of filaments and nodes over billions of years, forming galaxies, clusters, and superclusters. But the cosmic web is not as simple as simulations predict. Its structures are too large, its voids too empty, its filaments too coherent, and its walls too vast to form solely through slow, steady gravitational collapse. Something else must be at play, something that once pushed, pulled, twisted, or compressed matter across unimaginable distances. Cosmic quakes, rippling through dark matter scaffolding, could provide that missing ingredient. Imagine a low-frequency gravitational wave passing through a region of young cosmic plasma in the early universe. As the wave moves, it compresses matter in some regions, stretches it in others, leaving behind patterns, density contrasts, that serve as seeds for future galaxies. Over eons, these seeds amplify, filaments grow thicker, voids deepen, superclusters expand. These are not random patterns, they are echoes, fossilized remnants, of vibrations that once rattled the young universe. But the consequences do not end with large-scale structure. Cosmic quakes may also influence galaxy formation and evolution in surprising ways. Take galaxy spin, for example. Most galaxies rotate, but not randomly. Recent observations reveal intriguing alignments across vast regions. Galaxies separated by hundreds of millions of light-years showing similar spin directions. Such coordination should be impossible if galaxies formed independently under random conditions. But if they formed in the wake of a rolling cosmic wave, part of a universe-scale quake, then their motions would naturally align, spun into coherence by the shifting gravitational potentials. A cosmic quake would not rotate galaxies like spinning tops, but it could nudge the density fields in which they form, subtly guiding the direction of their future rotation. Over billions of years, this guidance becomes locked in, preserving the memory of the quake long after its passage. Another consequence touches the motion of galaxies themselves. Observations show that some galaxies move faster or slower than expected, as if pushed by forces beyond their local gravitational environment. This anomalous motion, often dismissed as measurement error, could instead be the residual drift from ancient cosmic quakes. Imagine a region of space-time that was compressed long ago by a massive wave. Galaxies caught in its path would accelerate slightly, their motions adjusting to the shifting gravitational field. When the wave passed and the universe settled again, those galaxies would retain their altered trajectories indefinitely, wanderers forever marked by a tremor that occurred billions of years before their stars even formed. But the most profound consequences may occur not on the scales of galaxies, but on the scales of galactic clusters and superclusters. Massive structures bound together by a delicate balance of gravity and inertia. Clusters are environments of intense gravitational interaction. Hundreds or thousands of galaxies orbit one another, immersed in vast halos of dark matter. If a cosmic quake passes through such a region, the gravitational potential within the cluster could shift subtly. Over time, this shift would cause galaxies to migrate, alter their orbits, or even trigger collisions that would not otherwise have occurred. In fact, some of the most extraordinary cluster structures, such as the bullet cluster, may be relics of massive gravitational disturbances. The bullet cluster appears as if two galaxies smashed through each other at unprecedented speed, with dark matter and gas separating in dramatic fashion. One explanation is a high-speed cluster collision. Another, more exotic possibility is that this region once experienced a powerful cosmic wave, accelerating clusters into each other with extraordinary force. Such cosmic quakes could also impact voids, the vast empty spaces between filaments. Voids are not perfectly still. They expand, evolve, and occasionally spawn new structures. If a cosmic quake passes through a void, it might stretch the region further, deepening it, preventing matter from accumulating. Over billions of years, these voids could grow far larger than gravitational models alone predict, exactly as we observe. Thus, the architecture of the universe, its largest walls, deepest voids, and most intricate filaments, may be not only the product of gravity and expansion, but the fingerprints of cosmic quakes etched onto space-time. But what of the smaller scales? Stars, planets, even life. Could cosmic quakes influence the formation of solar systems? It sounds dramatic, but the effects might be subtle. Slight distortions in the gravitational environment around molecular clouds, shifts in the collapse patterns of star-forming regions, variations in the density of dark matter halos, fluctuations in the background gravitational field. These influences could change how stars are born, how protoplanetary disks evolve, or how heavy elements are distributed. Over cosmic time, this might nudge the frequency of habitable systems, subtly guiding the emergence of life, not deterministically, but statistically. In this sense, if cosmic quakes exist, they may have indirectly shaped the conditions that allowed Earth to form, and with it, the rise of living beings capable of contemplating such ideas. There is a more profound implication still. Cosmic quakes may influence cosmic expansion itself. The Standard Model assumes expansion proceeds uniformly across space, but evidence increasingly suggests variations, tiny, yet measurable, in different regions. This is the core of the Hubble tension. Some regions expand faster than others. Some show unexpected gravitational flows. These anomalies could be the lingering motion from a slow, deep-seated universal quake, a rolling shift in space-time that has not yet fully settled. In this framework, the universe is not smoothly expanding, but rather expanding in patches, their rates influenced by past quakes, much like different regions of Earth rising or sinking after a massive earthquake. Such regional differences could lead to strange phenomena: misestimation of distances, apparent acceleration differences, temperature asymmetries in the CMB, large-scale anomalies like cold spots or power deficits. Each anomaly becomes a clue, a piece of evidence that the universe is still vibrating from ancient events. And what of the future? Could cosmic quakes contribute to the ultimate fate of the universe? There are three major possibilities presented by cosmology. The Big Freeze, expansion continues forever. The Big Rip, expansion accelerates until structures are torn apart. The Big Crunch, gravity overcomes expansion and collapses the universe. But if cosmic quakes exist, they introduce a new factor: oscillations. Imagine the universe as a drum, struck occasionally by massive events or internal tensions. Each strike sends waves across space-time. If those waves persist, fading, but never dying, they could interact with expansion. In some cycles, they might accelerate expansion slightly. In others, slow it. Over vast timescales, this could lead to a universe that does not expand uniformly, but rhythmically, influenced by the lingering reverberations of cosmic quakes. Perhaps the universe does not have a single fate. Perhaps it has a pulse, a universe that trembles, shifts, oscillates, subtly but meaningfully, might never truly settle. It could evolve in unexpected ways, with quakes periodically reshaping its structure, redistributing galaxies, altering expansion rates, and even influencing future cosmic phase transitions. And if cosmic quakes grow stronger over time, if the tensions in space-time accumulate rather than dissipate, then perhaps the universe may one day experience a quake so vast, so deep, that it triggers a new phase transition, restarting or reshaping cosmic history. A universe that trembles is a universe that lives. A universe that quakes is a universe capable of change. And change on cosmic scales is the engine of everything we see. In the next block, we will explore how advanced civilizations, if any exist or once existed, might experience, detect, or even attempt to harness cosmic quakes. And we will confront a haunting possibility that cosmic quakes may have erased entire civilizations from existence, leaving behind only the faintest echoes in the structure of the universe. If cosmic quakes can sculpt galaxies and whisper across the cosmic skeleton, then they also touch everything that arises within that structure, including civilizations. Life forms may be tiny, fragile sparks within an immense and trembling universe, but they are not exempt from its motions. If cosmic quakes exist, then every intelligent species that has ever arisen across billions of years has lived under the faint rumble of shifting space-time. Some may have survived these tremors, some may have detected them, and some may have vanished in the depths of their aftermath. To imagine how civilizations experience cosmic quakes, We must think on scales far beyond star systems. A quake of the universe is not a sudden catastrophe, at least not usually. It does not rip planets apart in a single moment. It does not unleash shockwaves through atmospheres or fracture planetary crusts. Instead, it operates through the slow, relentless shift of gravitational landscapes, the subtle migration of galaxies, and the gradual warping of cosmic expansion. For civilizations, these changes might unfold so slowly that countless generations pass without noticing, yet their long-term effects, spread across millions of years, could be profound. Consider a civilization emerging in a galaxy subtly drifting from an ancient cosmic quake. Its star systems move a fraction faster than cosmic models predict. Its local cluster migrates toward an unexpected region of space. Over thousands of years, astronomers might map this drift and conclude that their galaxy is caught in a gravitational current, a cosmic afterflow from some long-ago tremor. Their entire history is shaped by the wake of an event that occurred billions of years before their star was born. For young civilizations, cosmic quakes are invisible, but for advanced ones, those who master interstellar science and peer into the deep structure of reality, they may become an object of intense fascination, perhaps even existential concern. Imagine a species that learns to measure gravitational fields with unimaginable precision. They build observatories that float between stars, detectors stretched across moons, sensors buried beneath the crust of planets. They map space-time the way we map continents, and what they discover unsettles them. Anomalies that cannot be explained by local gravity, by galaxy rotation, by traditional cosmic models. Some regions of space expand faster than others. Some clusters drift as if pushed. Some filaments are stretched thin, as if pulled by distant forces. A pattern emerges, too consistent, too directional, too coherent to be random. They realize they are not merely observing the universe. They are witnessing the aftershocks of cosmic quakes, events older than stars, older than galaxies, older than life. As their understanding grows, so does their wonder. If these quakes shape the architecture of the cosmos, then civilizations themselves owe their existence to them. The location of their galaxy, the distribution of matter that formed their star system, the delicate balance of elements that led to life, all might trace back to distant tremors in the skeleton of the universe. But awe gradually transforms into apprehension, because if cosmic quakes shape the past, they might also shape the future. Civilizations may come to fear what lies ahead. A slow tremor in space-time could alter the trajectory of galaxies, bringing clusters closer together or flinging them further apart. If the dark matter halo surrounding a civilization's galaxy is stirred by a passing microquake, star-forming regions could shift. Spiral arms might flatten or distort. A cosmic quake affecting a nearby cluster merger could unleash gravitational chaos, triggering starbursts or depleting gas reserves needed for future star formation. Over millions of years, such changes could influence the fate of whole civilizations. But even more unsettling is the possibility that cosmic quakes could trigger local instabilities, events that play out on human timescales. For example, if a cosmic quake perturbs space-time gradients near a dense region, it might subtly alter the orbits of stars in the galactic core. Some stars might be nudged toward dangerously close encounters with others. Tidal disruptions could occur. Radiation bursts could follow. Civilizations living in the periphery might experience skies transformed, new stars appearing, old ones shifting, strange fluctuations in background radiation. Imagine a civilization that records starlight across millennia and notices something impossible: the cosmic microwave background temperature fluctuating, not dramatically but subtly, the structure of nearby voids expanding, the gravitational potential of their region gradually changing. They piece together the truth. Their region of the universe is passing through a weak aftershock of a cosmic quake that occurred billions of years ago. For them, a cosmic quake is not ancient history. It is a slow-moving event passing through their sky like a shadow. But there is another possibility, far darker and far more speculative. Perhaps some civilizations did not survive, not because cosmic quakes are violent, but because they change the conditions necessary for life. The stability of a galaxy influences its long-term habitability. Regular star formation provides fresh environments for life to emerge. Quiet galactic centers reduce the frequency of sterilizing events. Stable dark matter halos maintain gravitational balance. A major cosmic quake, especially one from a phase transition or large-scale dark matter redistribution, could disrupt all of these. A shift in a galaxy's trajectory might push it toward denser regions where supernovae are more common, increasing extinction events. A change in dark matter distribution might alter gravitational fields in star-forming regions, leading to unstable planetary orbits. The collapse or dispersal of molecular clouds might truncate star formation, leaving fewer habitable stars for future life. Entire civilizations could quietly fade as the cosmic environment around them drifts into instability. And what of civilizations far more advanced than we can imagine? Those who have mastered interstellar travel, harnessed the power of stars, or constructed megastructures around suns. How might they respond to cosmic quakes? Such civilizations would not simply observe cosmic quakes. They would predict them. They would map the cosmic web not as a static structure, but as a dynamic system vibrating with ancient events. Their detectors might sense faint gravitational resonances humans cannot imagine. They might build vast monitoring stations that stretch across light years, measuring the slightest tremors in space-time. And upon detecting the approach of a major cosmic shift, they might act. Perhaps they would evacuate unstable regions of space, migrating toward calmer cosmic neighborhoods. They might design their habitats to withstand gravitational fluctuations, anchoring them to the deep currents of the universe. Some may even attempt to stabilize their regions, using advanced manipulation of dark matter or gravitational fields to reduce the impact of incoming quakes. But there is something else, something that extends beyond survival, something that hints at a far deeper interaction. What if the most advanced civilizations tried not only to survive cosmic quakes, but to understand them, to decode their patterns, to interpret them as messages hidden in the structure of the universe? For a sufficiently advanced species, cosmic quakes might not seem like random disturbances. They might resemble the resonant modes of a vast cosmic instrument, subtle, intricate, patterned. The universe itself could be ringing with information, encoded in the frequencies of its trembling. Civilizations far beyond our understanding might treat these cosmic vibrations as data, deep time signals woven into the fabric of reality. They might decode stories from the early universe. They might uncover the signatures of past cosmic transitions. They might learn the history of the cosmos, not from stars or dust, but from the trembling of space-time itself. And perhaps, just perhaps, one of the greatest mysteries of cosmic silence could be explained by this perspective. The Fermi paradox asks why we see no signs of other civilizations. But what if the answer is that many civilizations were lost to ancient cosmic quakes, slow creeping catastrophes that unfolded over millions of years? What if the structure of the universe itself is responsible for the Great Silence? Civilizations emerging in unstable regions might have been destroyed long before they developed the technology to broadcast signals. Others might have lived their entire history under the shadow of cosmic instability, never lasting long enough to reach the stars. And the rare few who survived might have disappeared into the deeper currents of the universe, migrating toward regions where space-time is calm, leaving behind silent galaxies. In this view, cosmic quakes are not merely structural events. They are filters, cosmic sieves that determine which civilizations endure and which vanish. Life exists only in the quiet spaces between quakes, in the intervals of stability between vast, slow tremors. We may be lucky, or perhaps we are living on borrowed time. In the next block, we will explore the deeper consequences of a trembling universe, not just for life, but for the nature of physics itself. If cosmic quakes are real, then our understanding of time, space, and reality must evolve. The universe is not a static arena. It is a trembling, shifting ocean, and we are adrift upon its waves. If the universe quakes, if its underlying architecture trembles, flexes, and rolls across aeons, then the consequences are not limited merely to galaxies, clusters, or civilizations. They reach downward into the very foundation of reality, to the numbers and symmetries that govern everything from the orbit of moons to the fusion in stars, to the chemistry of life itself. A universe that trembles may be a universe whose physical constants are not constant, whose vacuum state is not fixed, whose cosmic rules are not eternally stable. And in such a universe, the deepest implications are not about where galaxies drift, but about whether the laws of physics themselves might one day shift beneath our cosmic feet. To explore this realm, we must start with a question that physicists rarely ask openly, because the consequences unravel everything. What if cosmic quakes alter the fabric of space-time in ways that change local physics? On Earth, an earthquake can alter landscapes, fracture bedrock, bend rivers, reroute entire ecosystems. But earthquakes do not change the chemical properties of carbon or oxygen. They do not alter the strength of gravity or the charge of an electron. They do not rewrite the rules of matter. But a cosmic quake is not a terrestrial event. It is a disturbance in space-time itself, rippling across the underlying fields from which all particles arise. If the tremor is strong enough, or if it intersects with delicate cosmic transitions, it could influence things far deeper than matter's arrangement. It could influence matter's nature. Every particle in the universe emerges from underlying fields. The electron comes from the electron field, the photon from the electromagnetic field. The Higgs field gives mass. The quantum vacuum binds everything. If any of these fields fluctuate on large scales, if they are distorted, strained, or reconfigured during a cosmic quake, then the constants that govern physics may shift ever so slightly. Tiny changes in constants can have enormous consequences. Imagine the fine structure constant, which determines how strongly light interacts with matter, changing by a fraction of a percent. Stars may evolve differently. Fusion might become more efficient or less stable. Carbon might be less likely to form. Water chemistry might become subtly altered. Entire biospheres could be influenced. Or imagine the gravitational constant shifting imperceptibly. Planetary orbits would adjust. Star systems could destabilize. Tidal forces might intensify or relax. Black holes could grow or evaporate at different rates. These changes would be tiny, too small to measure on human timescales. But spread across millions of years, they could transform the architecture of solar systems, the evolution of galaxies, and the fate of life. This possibility is not pure speculation. Some cosmological models predict that fundamental constants may vary across space. Observations of distant quasars suggest slight differences in spectral lines, subtle hints that the value of key constants might not be identical everywhere. These variations remain controversial, but they raise an astonishing possibility. We may already be observing the fingerprints of past cosmic quakes in the form of shifting constants across the universe. If cosmic quakes affected the underlying fields that define the laws of physics, then different regions of space might preserve different snapshots of physical law. Some regions may have settled after a quake into a slightly altered vacuum state. Others may still be trembling toward a stable configuration. For a civilization living within one region, the laws of physics feel eternal. But for observers comparing distant regions, anomalies might appear, differences in radiation spectra, strange variations in chemical abundances, unexpected gravitational behaviors. These oddities could be relics, echoes, of cosmic quakes that unsettled the vacuum state billions of years ago. Even more dramatic is the possibility that cosmic quakes could induce localized vacuum instabilities. At the deepest layer, space-time is a field with energy stored in its vacuum. The universe today exists in a stable, or possibly metastable, vacuum state. But the vacuum is like a landscape. It has valleys and plateaus. If a cosmic quake is strong enough, or if it resonates with quantum fluctuations, it might nudge a region of vacuum into a slightly different configuration. The result could be a pocket universe with slightly altered laws. This does not mean tiny universes budding off like bubbles. It means pockets of altered physical rules emerging within the same universe. Regions where certain constants differ, where certain particle interactions are slightly modified. Such regions might be invisible to us, or they might be the source of puzzling anomalies in distant cosmic structures. A galaxy whose chemistry seems strange. A cluster whose gravitational behavior is inconsistent. A void whose expansion rate differs subtly from its surroundings. These anomalies, rather than errors or coincidences, might be scars of cosmic quakes, fossilized evidence that the vacuum state itself once trembled. And this has profound implications for the past and future evolution of the universe. Consider the formation of stars. Stars require a delicate balance between gravity and nuclear force. Too strong or too weak, and stars collapse or fail to ignite. A cosmic, quake-induced shift in constants, even by a fraction, could create regions where different generations of stars form. Some might burn hotter, some might generate heavier elements, some might never form stable solar systems. This altered stellar evolution would then shape the availability of habitable worlds. Civilizations in different cosmic regions might arise under different physical rules, slightly different chemistry, slightly different astrophysical conditions. Their biology, technology, and perception of reality might evolve accordingly. Now imagine how such civilizations, if advanced enough, might interpret these differences. They might discover that the universe is not uniform. They might detect that the laws of physics vary from region to region. They might uncover evidence that these shifts occurred at different epochs, suggesting that the universe has not always been stable. They might realize that cosmic quakes are not merely structural events, they are historical events, and the universe preserves their memory not in rock strata or broken continents, but in the subtle, persistent fingerprints embedded in physics itself. But this leads to an even more profound question, one at the border of cosmology and philosophy. If the laws of physics shift, even slightly, then what is real? What is stable? What is permanent? To live in a trembling universe is to accept that nothing, even the rules, is fixed. Time itself may be shaped by quakes. The rate at which time flows depends on the structure of space-time and the energy within it. If a cosmic quake perturbs the vacuum, time might slightly speed up or slow down in affected regions. Not enough for beings inside those regions to perceive, but enough for astronomers millions of years later to detect via ancient light. Imagine a civilization studying distant galaxies and concluding that time once flowed differently there, that the cosmic quake altered temporal structure subtly enough to imprint its effects into starlight. This means cosmic quakes may influence the observable history of the universe, and if quakes continue to occur, even slowly, then the cosmic story is still being written, not in stars or galaxies, but in the evolving nature of reality. Perhaps the early universe was far more chaotic than we imagine, with quakes rippling through field structures as different regions settled into stable vacuum states. Perhaps the cosmos stabilized only gradually as tremors faded. Perhaps our constants are simply the current calm between waves, or perhaps we are in the midst of a long relaxation, settling from a quake that occurred billions of years ago. The Hubble tension, the dark flow, the CMB anomalies, these could all be signs that we live in a universe that has not yet fully quieted. But there is another, even more dramatic possibility. What if cosmic quakes are not merely consequences of physical processes, but drivers of new physics? A cosmic quake could trigger a localized phase transition, a shift in symmetry, a reconfiguration of fields. Such events could be the birthplace of exotic particles, new forces, or even new physical regimes. Regions influenced by cosmic quakes may evolve differently, developing unique cosmic histories. This opens the door to a staggering idea. The universe may have different physical chapters, epochs defined not only by temperature and expansion, but by the aftermath of quakes in space-time. A pre-quake universe, a post-quake universe, a universe still trembling, a universe preparing for its next shift. This concept suggests that the fundamental structure of the cosmos is not static, but ever-changing, shaped across ages by resonances, tensions, and the gradual settling of the vacuum. And if these quakes continue, if tensions are still building, then the universe may one day undergo a shift profound enough to alter its laws once again, not catastrophically, not instantly, but slowly, subtly, inexorably. Like continents drifting toward a new configuration, the laws of physics may drift over unimaginable timescales, guided by the deep tremors of a universe still finding equilibrium. In the next block, we will take these ideas to their extreme, exploring how cosmic quakes might reshape not only the physical universe, but the future of cosmic evolution itself. And we will ask the final, unsettling question: what happens if the next cosmic quake is not subtle? What if it is vast enough to rewrite everything? If cosmic quakes have shaped the universe we see today, if they carved its voids, twisted its filaments, influenced its laws, and filtered its civilizations, then one truth remains unavoidable. The universe is not done quaking. The story of cosmic trembling is not a closed chapter buried in primordial time. It is an ongoing process, a slow and ancient rhythm woven into the expansion of space itself. And that means we must confront a question that dwarfs every other. What if another cosmic quake is coming? What if the universe is building toward its next shift? This is not a question of superstition or poetic fear. It is grounded in the physical tensions of the cosmos, tensions building in dark matter structures, in the accelerating expansion driven by dark energy, in the delicate stability of the vacuum state, and in the gravitational interactions of supermassive objects scattered across the cosmic web. The next cosmic quake might be subtle, a slow roll of space-time adjusting to internal stresses, or it might be catastrophic on a scale beyond anything our universe has yet experienced. It might take 1 billion years to unfold, or it might already have begun. To imagine this future, we must explore the mechanisms through which new quakes could arise. We must examine how cosmic tensions grow, how they reach breaking points, and how the universe might respond. Let us begin with the most fundamental engine of cosmic tension, dark energy, the mysterious force accelerating cosmic expansion. Dark energy is not well understood. For decades, physicists assumed it was constant, a fixed pressure stretching space-time uniformly. But emerging evidence challenges this assumption. Observations suggest that dark energy may vary slightly across regions of space, or slowly evolve over time. If dark energy is not constant, then the expansion of the universe is not smooth. Some regions stretch faster than others, creating structural stress on the cosmic web. Imagine a drum being pulled in all directions, not evenly, but unevenly. Tension accumulates in certain areas. The membrane strains, distorts, and vibrates. The cosmic web, woven across billions of light years, could behave in similar ways. As dark energy's pressure increases, the filaments connecting galaxies may become stretched thin. Nodes of dark matter might strain under the competing forces of gravity and expansion. Eventually, something must give. Perhaps the next cosmic quake is the moment the universe readjusts, when space-time shifts to a new equilibrium under the influence of evolving dark energy. Such a quake would not be instantaneous. It would ripple across tens of billions of light years over hundreds of millions of years. But the long-term effects could be profound, accelerating some regions dramatically, slowing others, subtly altering the distribution of matter, reshaping galactic motion, and leaving structural scars that future civilizations might study long after the tremor fades. But dark energy is not the only source of potential cosmic instability. The dark matter skeleton of the universe may also be drifting toward critical stress points. Dark matter forms the cosmic web's underlying framework, holding galaxies in place like beads on invisible threads. But dark matter is not static. It flows. It interacts gravitationally. It oscillates. When two massive clusters merge, their dark matter halos can slosh and reverberate for billions of years. These reverberations may combine, amplify, or collide, producing large-scale turbulence that disturbs gravitational fields across vast stretches of space. Perhaps the next cosmic quake will begin with one such disturbance, an enormous redistribution of dark matter triggered by the collision of superclusters. Picture 2, galaxy superclusters, each containing quadrillions of stars, rushing toward each other over hundreds of millions of years. When they collide, the visible matter, gas, dust, stars, interacts violently, but the dark matter halos pass through each other, oscillating like colliding tides. This oscillation may release gravitational waves so enormous, so slow, so deep in frequency, that they propagate across the cosmic web like rolling seismic waves at the speed of gravity. Civilizations might experience the passing tremor as subtle variations in gravitational fields. Their star systems might drift or adjust their orbits over geological timescales. Their measurements of cosmic expansion might shift without warning. A faint deepening of voids, a stretching of filaments, or a mysterious migration of clusters might hint at forces far, far away. Such a quake would be the universe readjusting itself after a massive rearrangement of dark matter, an event of unimaginable scale. But still, there are deeper and more dramatic possibilities. The vacuum state itself, the field configuration that underlies all physics, might be drifting toward instability. If the Higgs field is metastable, as some theories suggest, then the universe is perched precariously in a false minimum of vacuum energy. Any disturbance, perhaps triggered by gravitational compression in collapsing superclusters, or by the accumulation of dark energy, or by rare alignments of quantum fields, could nudge the vacuum into a new configuration. This would trigger a vacuum phase transition, a universe-shaking event comparable only to the first moments after the Big Bang. In such a scenario, a bubble of true vacuum would form somewhere, perhaps smaller than an atom. It would expand at nearly the speed of light, converting everything in its path, space, time, matter, into a new state of physics. The laws of nature would change instantaneously inside the bubble. Atoms might no longer exist. Light might behave differently. Gravity might be altered. To any civilization caught within the bubble, the transition would be instant and final. No warning. No chance of escape. While this fate is unlikely on human timescales, the possibility that cosmic quakes could induce such transitions is deeply unsettling. It reframes cosmic trembling not merely as structural shifts, but as potential triggers for new epochs of physics. Epochs that could begin without warning, rewriting reality. But even without vacuum decay, cosmic quakes could drive dramatic changes through cosmic phase transitions of a gentler sort. Perhaps dark energy will change form, transforming into a field that diminishes over time, leading to a cosmic slowdown. Or perhaps it will intensify, pushing the universe toward the Big Rip, where expansion accelerates so violently that galaxies, stars, planets, and even atomic structures are torn apart. In such a future, cosmic quakes may be the final convulsions of a dying universe, space-time trembling as the cosmic web unravels, filaments snapping under accelerating expansion, clusters evaporating as gravitational bonds break. Civilizations living billions of years from now, if any endure for such unimaginable spans of time, might witness these last tremors. Their scientists might observe galaxies disappearing one by one, pulled beyond cosmic horizons. They might detect rising instability in dark matter halos. They might realize that their universe is entering its terminal quake, the last great upheaval before dissolution. Yet the future need not be catastrophic. A different possibility is that cosmic quakes will guide the universe toward new equilibrium states, cycles of tension and relaxation that shape cosmic structure indefinitely. A universe that quakes rhythmically might expand and settle in alternating eras, each quake redistributing matter, adjusting expansion rates, and sustaining a dynamic cosmic landscape for trillions of years. Civilizations might emerge during quiet eras and vanish in turbulent ones, only for new civilizations to arise again when the cosmos settles. History might stretch across quakes, epochs of life separated by deep time tremors of space-time. In this view, cosmic quakes are not destructive, but renewing, cosmic seasons guiding the evolution of structure. And if cosmic quakes influence physical constants, the universe could experience phases of slightly different physics. Some epochs might favor star formation, rich chemistry, and life. Others might be sparse, harsh, or barren. The universe could cycle between eras of creation and eras of quiet, each shaped by the tremors of space-time. This concept hints at a startling possibility. Cosmic quakes may be the heartbeat of an evolving universe, each tremor a pulse shaping cosmic history. If this is true, then perhaps we are living in one of the calm intervals, cradled between ancient quakes. Perhaps our ability to exist at all depends on the universe's momentary stillness, its temporary structural harmony before the next tremor begins. But how would we know the next quake is coming? The signs may already be present. The Hubble tension, the disagreement about the expansion rate, might be a symptom. The CMB anomalies might be scars of past quakes. The dark flow might be the residual drift of regions still relaxing from ancient tremors. The uneven expansion across cosmic voids might indicate tensions in the cosmic web. These might be hints that the universe is not fully settled, that the next cosmic quake is brewing silently across billions of light years. But the most haunting question arises when we consider the perspective of the universe itself. Are cosmic quakes a flaw, or a feature, a consequence, or a purpose? Perhaps trembling is simply what universes do. Perhaps no universe is truly stable. Perhaps cosmic quakes are natural expressions of evolving space-time, the way a planet's crust shifts or a star convects. If so, then the universe is not a static canvas. It is a living, changing structure, trembling, reshaping, growing, and we, tiny observers, exist only during one calm moment in its ancient trembling cycle. In the next block, we will bring everything together. We will examine the philosophical, existential, and scientific implications of living in a trembling universe. And we will confront the final question: what does it mean for a civilization, any civilization, to exist in a cosmos that may one day quake again? If the universe quakes, if space-time shudders with ancient resonances, if physical laws drift across unimaginable gulfs of time, if cosmic architecture bends to deep structural tensions, then the greatest question is no longer scientific, but existential. What does it mean to live in such a universe? What does it mean for beings like us, fragile and finite, whose entire existence unfolds within a momentary calm in a cosmos that may quake again? What does it mean for meaning, for purpose, for the stories civilizations write across the stars? To grapple with these questions, we must begin by acknowledging a truth both humbling and profound. A trembling universe is not a broken universe. It is not unstable in a way that threatens existence at every moment. Instead, it is dynamic. It is alive with motion. It shifts, adapts, settles, and reshapes itself. Cosmic quakes are not anomalies. They are expressions of the deep physical behavior of a universe still evolving. In such a cosmos, stability becomes relative. Permanence becomes an illusion. What feels eternal to us, stars, galaxies, physical laws, may be transient on cosmic timescales. The universe is ancient, but it is not static. It grows, it stretches, it adjusts to tensions we barely comprehend. This realization forces us to rethink our place in the cosmos. Human beings evolved in a quiet corner of one galaxy, sheltered from cosmic extremes. Our star is stable. Our region of the Milky Way is relatively calm. We live in a cosmic lull between ancient tremors, one that enabled planets, chemistry, life, complexity, consciousness. Were the universe trembling violently today, life as we know it could never have arisen. Our existence is tied intimately to the universe's momentary stillness. And yet, the evidence suggests that stillness may be temporary. This does not mean disaster is imminent. Cosmic quakes operate over millions or billions of years, timescales so vast that even entire civilizations might come and go without perceiving more than a whisper of change. But the possibility of future trembling invites reflection. It forces us to confront the fleeting nature of cosmic conditions. And at the heart of this reflection lies a paradox. The very instability of the universe may be what made life possible in the first place. If cosmic quakes helped shape the large-scale structure of the universe, sculpting the cosmic web, distributing matter, influencing galaxy formation, then the environment in which life arose is itself a product of trembling. If cosmic quakes influenced physical constants, nudged vacuum configurations, or guided cosmic phase transitions, then even the laws of physics that permit life are shaped by this trembling. We exist because the universe quaked. This idea reframes our relationship, not just to the cosmos, but to physics itself. We often think of physical laws as eternal truths, but in a trembling universe, laws may be stories still being written, chapters shaped by deep time events. The constants that feel absolute may be temporary harmonies in a cosmic symphony that shifts across ages. This leads to a profound philosophical implication. Meaning is not diminished by cosmic instability, it is enriched by it. To exist in a trembling universe means to exist in a universe of change, evolution, and emergence. It means to be part of a story far larger than human history, or even biological evolution. Every star, every molecule, every galaxy is part of a dynamic dance that stretches across billions of years. A trembling universe is not hostile, it is creative. Yet we cannot ignore the existential weight of cosmic quakes. For any civilization advanced enough to understand the universe's long-term instability, the realization must be staggering. Their sciences might reveal that cosmic quakes shape their past and may shape their future. They might discover that their cosmic neighborhood drifts along gravitational flows created by ancient tremors. They might find evidence of future quakes, slow, creeping distortions of space-time building tension across the cosmic web. Such civilizations might confront questions we rarely consider. How do we define permanence in a universe where even laws may change? How do civilizations prepare for changes that unfold over millions of years? Is it possible to migrate to calmer cosmic regions, avoiding future quakes? Could the trembling of the universe be decoded, predicted, understood as deeply as we understand stellar evolution? And if cosmic quakes are inevitable, how does a species build meaning, culture, and identity within this vast dynamic landscape? These questions shift cosmic trembling from a scientific curiosity to an existential framework. But there is another, deeper level of reflection, one that emerges when we consider the possibility of cosmic quakes as cosmic messages. The universe vibrates, gravitational waves ripple through space-time, dark matter oscillates through filaments, cosmic expansion accelerates unevenly. The cosmic microwave background contains patterns, subtle, strange, hinting at asymmetries still unexplained. To advanced minds, these may appear not simply as physical consequences, but as information encoded in the universe's trembling. Consider the idea that cosmic quakes preserve memory. Each tremor modifies the cosmic web, leaving behind structural patterns. These patterns persist for billions of years. They are fossilized in galaxy distributions, void shapes, cluster alignments. They may be readable, like cosmic hieroglyphs, by civilizations capable of interpreting them. Perhaps cosmic trembling is not random. Perhaps it carries the history of the universe, encoded in the structure of space-time. For beings capable of deciphering these patterns, cosmic quakes become a window into the past, a way to reconstruct epochs long before galaxies existed. Humanity is not yet such a civilization, but we may one day become one. If cosmic quakes leave measurable fingerprints on cosmic structure, then future astronomers may decode ancient events through precise mapping of the cosmic web. They may track gravitational flows tracing back to tremors billions of years old. They may find that the universe's trembling is not just motion, but memory. And once a species realizes that cosmic quakes encode the history of reality itself, the trembling of the universe becomes something far more profound, a narrative, a record, a cosmic autobiography written across space-time. This transforms cosmic quakes from physical disturbances into carriers of meaning. They become the language of the universe, its method of shaping, storing, and transmitting its own evolution. But even this interpretation is overshadowed by the ultimate existential question: how should we live knowing that the universe may quake again? Some might see this as a reason for despair. Why build? Why strive? Why reach for the stars if cosmic instability could rewrite reality itself? But this perspective misunderstands the scale of cosmic trembling. Cosmic quakes do not erase meaning. They enhance it by contextualizing our existence within a vast, dynamic cosmic story. Meaning is created in the present, within the moment of stillness we inhabit. The fact that the universe may change only heightens the preciousness of this moment. And perhaps that is the ultimate message of a trembling cosmos. Value the now, for even the universe does not remain unchanged forever. Another perspective, more ambitious, perhaps more optimistic, is that civilizations may one day learn to adapt to cosmic quakes, to anticipate them, to understand space-time deeply enough to navigate shifting fields, migrate across cosmic flows, and endure changes in cosmic structure. A civilization advanced enough to harness gravitational waves or manipulate dark matter might even influence local space-time, stabilizing their region or riding cosmic quakes like surfers on an ocean of stars. Such civilizations would not be victims of cosmic trembling, they would be participants in it. And this raises a final, extraordinary possibility. What if cosmic quakes are not simply something civilizations must endure, but something they can one day help shape? If space-time is dynamic, if vacuum fields are malleable, if cosmic structure responds to deep gravitational influences, then perhaps sufficiently advanced civilizations could one day participate in the shaping of cosmic evolution, not controlling the universe, but interacting with its deepest rhythms. They might amplify or dampen local quakes. They might influence the flow of dark matter. They might manipulate gravitational fields on intergalactic scales. They might help guide their region into stability, a cosmic engineering project on the grandest scale imaginable. In this view, civilizations become collaborators in the universe's evolution. They do not merely witness cosmic trembling, they help write the next chapter. And perhaps that is the final message of a trembling universe. Reality is not fixed. It is something that can evolve, and something we may one day help shape. To exist in a quaking cosmos is to exist in a universe of possibility. It means living in a reality that grows, shifts, tells stories, remembers ancient events, and anticipates future ones. It means that the universe is not a static arena for life, but a dynamic participant in the story of existence. And we, though fragile, though fleeting, are part of that story. We live in the quiet between quakes. We arise in the calm between tremors. We think, create, love, discover, and dream in a moment of cosmic stillness. And perhaps that moment is enough. Perhaps that moment is everything. Thank you for watching. If you enjoyed this video, leave a like and share your thoughts in the comments. Send it to someone who you think would enjoy this topic too. And of course, subscribe and turn on the notification bell so you don't miss the next videos. See you next time.